Great. Hello, everybody. My name is Andrey, and I'm really proud to be here. So today we're going to speak about GPUs. I've been an iOS developer for 7 years right now, and I barely touched UI kit throughout my career because most of my time I spent developing game engines, or now we make apps full of machine learning and computer vision. So basically, all of my career I've spent writing metal shaders, and today I'm going to show you that it's not that hard, because I see a lot of people thinking that it is really complex technology that is hard to approach, and all of those people are simply contributing to my imposter syndrome, because I know that it's not that hard, but everybody thinks it is. So today we are going to kind of bust the myths about it. But in order to better get an idea of what the GPU is and how it works, I think it's important to kind of look back at the history of how rendering evolved and get some insights of why GPU is built right now the way they are built. So we'll start with 1977, where Atari 2600 was released, because it was the first notable system which has separate hardware for the graphics. And it only had 128 bytes of RAM, and it, of course, couldn't never fit a frame in RAM, because it was like the whole hardware that it had, including OS and stuff. So the graphics had to be generated like in real time, like literally. So the TVs back there was working the same way. So they was scanning the image through the electronic beam, like line by line. And once the portion of image was scanned, it was staying on the TV until the kind of electronic beam went the round trip and kind of gets back and redraws it. So the problem was that Atari 2600 could only display like 5 objects at one time. And that, of course, wasn't enough even for games in the 70s. So the way developers kind of baptized it, they had to move objects as the TV was scanning the image. So once the beam passed the object, they moved it further so they could scan it. And then once the row is finished, they returned objects in their initial positions and then returned back. And now we complain about the Xcode bugs that it has. So back there, it was way harder. So in this way, they could achieve like running a lot of objects. This is the screenshot from the Space Invaders. And there is actually very nice book regarding this topic. Another fun thing is that they didn't have enough time to process like inputs from the gamepad or computer game logic, so they had to kind of include fake lines where they didn't kind of process the image, and instead they were processing inputs. And the Pitfall game developers didn't have enough time even more, so they had to kind of create the huge ground and huge trees so they can have more time computing what the player wants to do. The next iteration was NES. What they tried to do is they wanted to replace the picture processing with the tiles. So what tiles were is a simple, small piece of memory that is very fast, and the whole kind of image was processed by tiles. That has provided additional opportunities like collision detection, but was very limited, and that's why all of the games from that era looks a bit like square. After that, there were 3D solids, the first hardware, but it was very expensive and mostly limited to professional simulators. And the first GPU, as we know, was only released in 2001 by NVIDIA. It was called GeForce 256. It was barely programmable, but it was very fast, and it was very first piece of hardware that you could buy and install on your PC to accelerate vertex graphics. In 2001, they released GeForce FX and basically introduced the concept of shaders. We'll be covering it hardly today. And right after GeForce FX was introduced, it started obviously that GPU are going to space in terms of performance, especially compared to CPU, which went back. And if we saw on the trends, we'll see that the G-flops metrics is like a metrics how you evaluate how performant the hardware is. Were like 6 times per year, but the clock speed actually went down. And that's because the amount of transistors went up. From here, we can see that GPUs are massively parallel machines. They're very used to solve the problems that are friendly for parallelism. And to understand why, we have to understand like why, how the rendering currently goes. So the modern rendering process is like a key to understand why GPU is so performant. GPUs itself are very limited in what they can do. They're very dumb hardware. They don't have an OS. What they can only do is to render triangles, lines, and points. And it's highly optimized for floating point operation, so that's why GPUs are not used, for example, font rendering, because the precision is simply not enough. If you ever played video games, then you know that all of the 3D objects consist of triangles, or how they call them, polygons. And in order to get this drawn on a screen, you're gonna have to do 2 things. First of all, you have to put all of those vertices somewhere, and then just fill it with something. So the positioning is done by vertex shader. This is like very common, but it is also very simple shader. That only thing it does is just transforms every vertices from the model into the screen space. So it gets the triangle from the model coordinate space and reverses it into your monitor's one. So once each triangle gets on the screen, the rasterizer comes into play. What the rasterizer does is kind of overlaps your triangle with a grid of pixels and chooses the only pixels that overlap with the triangle you have. And then it calls the fragment shader for each of the pixels that are overlapping the triangle. So what the fragment shader is still a very small program that is launched for each pixel parallelly on the screen. To better understand it, let's imagine that we'll draw 2 triangles that fill all of the screen and see how vertex shaders can help us draw something. So the most stupid fragment shader you can imagine is like returning solid color. So if you return red, your screen will basically turn red and you will see like the whole screen with the same color. But if you try to be a little bit smarter, you can calculate the, for example, length to the center of the screen and use it as a red channel, and then you'll see like the gradual gradient. What you else can do is that you can pass each frame a sinus of time, and you will see then an animation of the screen, because each frame you'll see a different value and the fragment shader will be drawing it. But what most of the time it do is just simply takes the textures and put it in a needed position onto the screen. The idea of programmable images were actually before the shader started. So the guy called Paul Hegbert in 1984 launched a challenge where he proposed to kind of create a code that fits on a business card that can actually generate an image, and that's what his first image he did. But nowadays, people do amazing stuff writing only fragment shaders. All of those images are actually animated, and they didn't have any image, any texture, or any 3D model. So all of those are generated with code, with mathematical formula. So you can get the flames with the 66 lines of code only using fragment shaders. And this is really powerful technique that transformed the world in a way we know it. So all of those fancy video games are basically powering by the shaders technology, where it is as simple as launching small program per each pixel and ask it to return the color for each pixel. So what Apple has to offer, that's the most interesting for us since we work on Apple platforms. Actually, we've been blessed with having very good GPU support since 2007, since the first iPhone released. It supported OpenGL ES. And at that time, it could render comparable graphics with PlayStation 1. When the iPhone 4 was released, the OpenGL ES2 support landed, and we saw the beautiful games like the Infinite Blade. And throughout that time, a lot of frameworks and game engines released, because OpenGL was kind of the only way to proxy to OpenGL. When iPhone 7 released, OpenGLS 3.0 was introduced, but nobody really cared. And there are multiple reasons for that. First of all, it's Vulkan. Vulkan was announced by Kronos, this kind of committee behind the OpenGL, in 2015, and Apple was originally in a working group. The important thing to understand is OpenGL is not a library. This is sort of a standard that the vendor has to kind of conform to for the hardware and the software, and the Vulkan is a standard as well. And as we know, Apple doesn't like standards, doesn't like playing in games, so they decided to introduce their own API. It's called Metal, and this is what we are going to kind of focus on today. So the key aspects of Metal is that it is designed to be very low CPU overhead. So this is how it compares to, for example, OpenGL or even more high-level frameworks. It features all of the modern GPU features you can imagine, from tessellation to instance rendering and stuff. It is designed to make expensive tasks less often, so you move redundant work in the initialization stage and then do less throughout the frame. It's very optimized for CPU behavior because you can parallelize GPU and CPU, so since it's physical devices, you can prepare your next frame while GPU renderings the previous one. And it's very thin API that we'll cover in the details today. So in the core of the API of the Metal is MTL device. It basically represents a single GPU. In order to get it, you usually get MTL create a system default device function, but it's not a singleton object. In iOS, it actually kind of is, but if you use Metal for Macs, Macs can have multiple GPUs, one for high power processing, one for low power. It can have external GPUs, and by deciding which MTL device you will use, it will define where the code will be executed. And the important thing to understand about the Metal API is that extensively uses the pattern called dependency injection. So all of the objects are kind of created out of other objects. And the next key object is the common queue. The common queue is something you can create out of device. You just call a method called makeCommonQueue, and this pair is often referred to in Metal context. So these are two core objects that you need to actually process something on a GPU. So what the common queue is basic queue from the computer science that you all know. You can submit something there, and it will be executed in the order that was submitted. The important things to understand about it is that you are not the only one who submit workload there. So Apple do it as well. For example, when you use a map kit, they submit to the common queue things to render maps. They submit something to from their core logic. So you have to remember that you are not alone, and you will have probably need to wait for some time until your comments will be executed. So those specs that you see here being submitted to the queue are actually common buffers. Common buffers is like storage objects for comments. Once you fill the common buffer, it's actually nothing happens. It only starts executing once the common queue starts the order is for this package. To create a common buffer, you have to call makeCommonBuffer function. So you get kind of an empty package that you have to fill. So what we can fill it with? There are multiple types of comments, like render comments, bleed comments, and compute comments. So render comment is pretty straightforward. You can just render triangles or lines or points. Bleed comments are for copying, for extra fast copying from one texture to another. And the compute comments are for general purpose stuff. We'll see how it works later. In order to fill a comment into the common buffer, you have to use a special objects called encoders. So for each comment type, you have a dedicated encoder that you have to create out of common buffer. So you see pattern here. You create objects out of objects that you already have, and then use it, and then end it before you can create another one. So for example, for render comment, it will look like this. So we'll take our empty package that we just got from the common queue and create a dedicated encoder for that. And the process of creating a render comment is very close to crafting in video games. So you have slots where you can put something and then just ask encoder to bake something out of it. But the one ingredient is always has to be there in its pipeline state. What pipeline state is, it represents the GPU state that is needed to be in for the current command. It is composed out of shader functions that we covered earlier, and each pipeline state has its own optional parameters, for example, textures or maybe some constants as well. Usually, you have to kind of create the pipeline state once in the initialization stage of your app and save it later for like reuse. In order to create that, what you do is you create a descriptor and assign vertex function and fragment function for the render state that you can obtain from library. And then you just ask the device to compose the pipeline state for you and store it somewhere, usually in a property. So once you get it, you just put it in a first slot calling set rendering pipeline state, and this is just the first ingredient that we'll need. After that, you can add, for example, the geometry buffer, so this actual vertices of your 3D model. Then you can add maybe uniforms or a texture to cover your model with. You can use dedicated methods like set buffer or set fragment buffer for that. And once everything is in place, you just call draw primitives. And what really happens is your kind of package gets filled with one command. Nothing actually getting drawn on a screen until the package will be submitted to the queue. So you can further proceed to creating commands. You can assign another state or another geometry, call draw primitive once again, boom, and you'll have another command. So once you're finished with filling your buffer with any kind of commands, you can interchange types of commands. You can first encode the rendering command, then you can use the bleed command, and then just compute and interchange them the way you want. You have to call end encoding on the encoder, so to indicate that you are done filling this package. Until you do it, you cannot submit the command buffer. And the last stage is just to call commit on our filled package, just so it gets delivered to the command queue and executed. In order to wait for the results to be ready, you have to call wait until completed, but it's actually considered bad practice because that prevents you from having CPU-GPU parallelism. You can prepare more stuff until the previous commands are executed on a GPU using your CPU, which is stalling. So what's advised is to use add completion handler function to kind of get the callback once the command will be done. So let's see how to code something yourself. Maybe not rendering, because rendering is not really applicable for most of the iOS developers. It's mostly used in a video games industry. What you can do is that you can get leverage of what's called GPGPU, which stands for General Purpose GPU, to, for example, implement machine learning algorithms, or maybe some computer visions, or maybe you want to create a photo editor with fancy filters like Instagram has, which actually what is going to do right now. But before that, we'll dig into history once again. Yes, I'm a boring guy. The early GPGPU days started similarly when a first programmable GPU were released. What is also was done by PhD guys who was doing like computer graphics as their primary research. And it was a funny time because financial companies hired game developers to implement very fast solutions for their problems. The term GPGPU originated when in 2002, when GPGPU.org was released. It was a website where enthusiasts tried to use GPU for general purpose computing. What they tried to do is to simulate physical collisions, chemical reactions and stuff using parallel instructions. And the way they did it is that they tried to encode their data into the textures, so putting each float into the separate channel and then reinterpret it during the rendering. So they were seeing like, oh, on a pixel 5 there is a 2, that means something, let's interpret it in that way. But in 2007, our beloved NVIDIA released CUDA, which actually changed the game. So now from cryptocurrency mining to machine learning, most of that stuff is done throughout the CUDA. CUDA was the first GPU architecture and software platform that is designed for parallel computing. It was a C++ language for GPUs and started like a whole new industry of very fast computations. What CUDA initially did is that they introduced a very simple concept of compute shaders. They took fragment shaders and said, hey, we don't really need to use them for pixels on a screen. What we can do is just feed the fragment shader an arbitrary ID instead of its position and say in get it compute anything else. So what we'll do right now, we'll write our own compute shader, which will implement the brightness filter on the Instagram, right? So we can do our images more bright or more dark. But we'll have few prerequisites before we proceed. First of all of the code you'll see will be written with the Alloy library. But don't be scary, this is the library I developed for 3 years right now, and it has very important principle that it stands on, that it has no new concept. So it is not a wrapper library around the metal. It's still the same metal, same types. It's just a bunch of extensions that makes your code look more Swifty and more idiomatic. And it doesn't have any performance overheads. So what it essentially does is just transforming outdated Objective-C-like API to some modern stuff, but you don't have to learn anything new and you don't pay anything. It's just a more swiftier way to do stuff. Another thing we'll learn today is an encoder pattern. It doesn't really exist in the world, something I kind of imagine for myself to organize my code. What essentially encoder is just a class that represents all of the needed information for the particular shader. So it knows how to create the pipeline state for the shader, and it knows how to encode the shader into the package. So our first step will be to actually create a compute pipeline state. It is like very easy. We have to introduce our class. It will be called brightness because it will stand for the brightness shader. And what we'll want to do is to store our compute pipeline state somewhere in the properties of that class using the library as an injection, because this is where the shader is located. What it looks like is basically a single line of code where we just ask library to get us a compute pipeline state for the brightness shader. This is the name, which you see the passed as a string, has to correspond to the shader name that you'll write in a shader code. We'll see it later. Another thing we'll have to do is introduce encoding API. So what encoding does is just basically fills our command buffer with the instructions on how to do the actual brightness. And the way it works is we have to first create the encoder. Since we are doing a compute shader, we'll need a special kind of encoder called MTL compute common encoder, and it will look something like this. So we'll have a command buffer where we call compute, and we'll have to pass a closure where the system will provide us an encoder that we are going to use. And in order to kind of craft a command for computing, we'll have to first put our ingredients in. So we'll start with the textures. We'll have two textures as an input. First will be the source texture. The texture will be actually processing, so it's our image. And the destination texture will store the results for that. We'll also have an intensity, like it's a constant identifying how much of a brightness we want to bring in. So we just put the texture first by saying encoder set textures, passing the array of textures that we want to use, and that's all we need to do. The second step will be to provide an intensity for the shader. That is as simple as ever. You just press set intensity at 0 index because it's the first constant we'll have to use, and that's it. You are set the constant. Last step is to assign the pipeline state. Assigning pipeline state requires two steps. So first of all, you will have to assign the pipeline state yourself. And another thing is that you have to tell the GPU how much of a threads you want to launch. And in our case, we want as many threads as pixels in our image, because for each pixel, we want our dedicated thread that will transform the pixel in an image. So we just say dispatch to D, we pick our pipeline state that is stored previously in a property, and we say exactly, so how many threads we want, we say destination.size. So this is the amount of grid we'll use. And that's it. Once we get it all done, we have an encoder that's set up, and our command buffer has a one comment. But the problem is that nothing really happens at that moment. So you only have the package with something inside. You have to kind of launch it to the GPU. But before doing that, we have to write GPU instructions. GPU instructions are written in a metal shading language. This is a C, C++ subset. Basically, it only limits to writing basic C functions with some special keywords. This is the shader we are going to write, but we'll split it in smaller pieces just to better understand what's going on. First of all, we start our shader with saying kernel. Kernel stands for compute shaders, but you can also write here fragment shaders if it's a fragment shader, or a vertex shader if it's a vertex shader. Next, you declare your arguments. Your arguments currently are textures. It's input and output. And we also specify the access we're going to use it with, because this way Metal can optimize stuff. And if you say that you only write to the texture, it will use the cache more aggressively, and you will see even more performance. The last input that we'll use is factor. This is still our intensity, just with a fancy name. So this is the multiplier that we're going to multiply our pixel with, and to kind of get the expected results. And the last step is position. Position, it kind of indicates where is the location of the thread, so you can know which pixel to process with each individual thread. And you can also ask Metal for other meta information, not only the position of the thread, or you can also ask for the position of thread groups or how many threads there are, but this is more of an advanced technique. For the simple stuff, we need only the position of the thread. So first of all, what you have to do is you're going to read the pixel that you need, and you use position for that. So you use position to read the pixel from the texture. Next, what we are going to do is we are going to multiply it by a factor in order to kind of morph the image for a more brightness way. If it's more than one, or if it's less than one, it will be more darker. And write it back, but not in the original texture, but rather to the output texture. It's another one. Okay, so now we got our shader ready. We actually want to launch it and see what the results are. In order to do that, you have to do very few things. First, you have to do initialization stage. It consists only of 3 lines of code. The first one is we create a context, which basically stores our device and a command queue, as you remember. Then you create a library for brightness.self, so you pass type of the encoder just to get a needed library for your bundle in case your encoder sits in a framework or somewhere else, or you can just pass a bundle that you want. And you create your encoder that you just wrote by passing the library as an injection, so it could extract the compute pipeline state and prepare himself for the encoding. And the launching is a very simple process. So first of all, you get to prepare your textures. What you do is that you convert the CG image to texture using the context built-in method. And then you create the matching texture for the destination one. So it will use the same size, the same height, the same width, the same pixel format. But we say that the usage will be shader right, so we get more optimization from the Metal side. Next, we'll use the schedule and wait method. This is very similar to how encoding works. So you will pass a closure where you will receive a buffer that you will have to fill in. And the filling the buffer is just as easy as calling our encoder. The method that is being introduced, it was an encode, just so it can put the actual command inside. And that's it. Once you finished with that, your command went to the execution and now ready to be executed on a GPU. Once you wait it to the end, either by saying schedule and wait, or if you want to be more fancy and utilize parallels even more, you can just say schedule and then subscribe yourself to the callback of the buffer, you just call the output texture.cg image to convert it back to the CG image, and you can see the results. So can we make maybe straight usage out of what we did right now? Of course, you can now demyth Airbnb fake photos. You can just pass lower exposure just to see what the real room will look like, not like the paradise, just a regular room. Or if you're an Airbnb host, you can do the other way. You can pass a multiplier more than one to make an illusion that your apartment is the best place in the world. So for the last part, I have a few tips for those of you who are brave enough to start doing something with the GPU. So first of all, you gotta remember that GPU is a separate device that stands like physically outside of CPU. And that's why not only you pass data between two languages, from metal chain languages to Swift or Objective-C, but only between two physical devices. So if in case you pass instructs, you gotta remember that Swift doesn't have a standard for memory layout. So that's why you have to use custom Clang attributes to preserve it. Next, you gotta remember that when you fill common buffer, nothing really happens. You're only encoding commons. So when you mistakenly thinking that calling draw something will draw something, it's not. It just will put a comment inside a common buffer, and you have to wait, and the waiting time is kind of undetermined because you are not alone submitting the comments. You have to keep the code divergence to minimum, so GPUs aren't really good handling if conditions, because all of the threads are working parallelly, and they have to be kind of executing the same set of instructions. GPUs are better used for floats. It doesn't support doubles at all at iOS, and using ints are usually better to be avoidable. You should calculate thread group size thoughtfully, but this is more of an advanced tip. The cache a reusable object, so if you create a pipeline state, don't waste it so the ARC can pick it up for garbage collection. You just put it somewhere in a property just so you can reuse it every time you need it. And usually you shouldn't wait for GPU to wait for the execution. What you should do instead is that you should subscribe for the completion handlers, just so while the GPU does something, you can actually utilize your CPU for something useful. So that's it for today. I hope you enjoyed the talk and probably will try something metal yourself today. You can follow me on Twitter to get the slides and the code for this talk, for this presentation. I will post it there today. And I actually think we have some time for the questions. This is unexpected, but I tried my best. Okay, so the first one is, can you have a live demo of Hello Triangle? Not right now, since we have a limited time, but we can hack it together if you want to after the presentation. What kind of calculation should on CPU part, and what should be doing on shader side? So this is actually a very challenging question, but generally you decided by whether or not your algorithm is friendly to parallelization. It can be very obvious and can it not be really trivial to detect it, but general rule is that if the algorithm involves a lot of dependency, like it features a lot of semaphores, mutex, conditions or waitings, or if it's a loop where one iteration depends on the previous one, this is not what is friendly to the GPU. But if you have a workload that, for example, for loop, where each iteration doesn't depend on anything but the, for example, iterator, this is a very good sign for this to be on GPU. How difficult is to migrate an existing OpenGL code to Metal? Is it a full rewrite? Another related question, is it worth going for that migration in terms of performance? Okay, so yes, it is a full rewrite. but it's not hard, and I will try to explain why. So once you get into one single GPU API, it can be DirectX, it can be Vulkan, it can be OpenGL, it can be Metal. The thing is that they all work the same. So just the same paradigm, same concept, same common buffers, queues, shaders everywhere. Same names for uniforms and stuff. So once you get along with the OpenGL, it's very easy to convert to Metal, because if you have an OpenGL code base, that means you already understand all of the needed concepts for Metal. Metal doesn't bring anything new to the table compared to what OpenGL have. But and actually, the performance sometimes may be even worse outside of what Apple claims, because Metal has like some behaviors that differs from the OpenGL, but you still definitely should do it, because OpenGL is officially deprecated by Apple. So maybe in 1 or 2 versions of iOS it will be completely removed out of system, so your app will not be maintainable anymore. So you should start now, and especially given that OpenGL implementation of iOS 13 is very buggy, so your users are likely to experience problems right now if you have OpenGL codebase.
Yeah. Okay. Thanks, Andrey.